Okay,
Okay,
perfect.
can you see the presentation?
Yeah, looks great. Okay.
Okay, good morning. I will be quick, I promise. You already have seen the scientific goal of the Hermes Pathfinder mission. These goals, from a technological point of view, they impose some kind of ambitious engineering goals. What we need is a fractionated space assets by means of more satellites in order to provide short time to orbit, mission flexibility, and also to contain costs. The mission architecture is highly affected by such requirements. We have a lot of constraint. Hermes has to triangulate GRB in the sky, so it's easy, and it's a consequence to reason about satellite triplets. We need in part a very fast communication, at least for the communication for an early warning of a GRB observation. But we have also a large data volume. After the first observation, a large amount of data is collected. And we need some control authority while we need to contain costs. In the Hermes Pathfinder project, then we are speaking about 6 satellites with a 3U form factor CubeSat class. The expected life of the sensor also determines the duration and the timeline of the mission. After 1 month commissioning time, the expected life is 2 years in orbit per satellite, plus, if it's possible, some sort of extension. The performance of the mission are largely affected by the mission analysis. We have 3 degrees of freedom, basically, for each satellite: the nominal orbit, the injection strategy, and the pointing strategy. If for such a constellation, we have no control on the center of mass, we have no propulsion on board, also because propulsion is a very, very high voice in the cost of a satellite. Then our 6 satellites are in a loose formation, and the orbital dynamics affect largely the position of the spacecraft along the mission. Also, we have some cap on the orbit due to the sensitivity to the environment of the sensors inside the payload. And we need to have an overlap in the field of view of the satellite in order to guarantee a correct triangularization of the GRBs. We had to perform a very careful trade-off about also on the nominal orbits. We have, of course, some sources of disturbances on the sensitivity of the payload, on the quality of the measurement made by the payload, speaking about the South Atlantic anomaly, but also the polar region in which high-charged particles may concentrate. We restricted the search on low Earth orbit around the equators and some synchronous orbits. I mentioned the orbital dynamics because even if you release in orbit some satellites in close position, natural disturbances and the orbital dynamics make them drift a lot. In just 3 days after the release, we can have, if we release 3 satellites at once, we already have a baseline that is larger than 1,000 kilometers. And along 2 years mission, each triplets, the triplets that you release on orbits basically mixed with each other. such in the long term, as you can see on the right, basically the relative position of the satellites can vary a lot. Of course, in a band along the orbital plane that you select at the beginning. The performance is also affected, of course, by the pointing strategy. You have in order to detect in the sky a GRB, that GRB should be seen by at least 3 satellites. Of course, more is better. In the Pathfinder mission, we have just 6 of them, and then we have to carefully plan the pointing routine of the satellites. We evaluated several strategies. These are just the last 4 options that we evaluated. What has resulted is that the optimal strategy is a sort of inertial pointing, optimized and rescheduled weekly or bi-weekly. Basically, we optimized for each week the triplets that must act together, since basically the 6 satellites continually mixed. For each week or couple of weeks, we can determine the best triplets and the best pointing for each triplets in order to maximize the area of the sky that is continuously looked at. Of course, it's along the whole mission is not observed the very same area of the sky. Then along the whole mission, more or less, the whole celestial sphere is observed. Here you can see the comparison with of such optimized pointing strategy on the right with respect, let's say, an inertial pointing, but not optimized and fixed along the whole mission. You can see that you have an increment in both the baseline and the expected number of GRB that you can observe. Indeed, with this optimized strategy, the small constellation of 6 satellites of Hermes Pathfinder become robust even to the loss of 1 or even 2 satellites, the complete loss I'm speaking about. Also, the orbit injection strategy matters, of course. In fact, since it's hard to obtain a dedicated launch for each satellite, but it's easier to launch at least 3 satellites at once. If you release in the sky 2 triplets, you can find the optimal angular separation along the orbital plane in which to release them in order to maximize the scientific return. Speaking about the data transfer, well, the peculiarity of the communication required by such a constellation is the, let's say, a GRB early warning. It's a short burst of data released whenever a GRB is observed in order to provide a warning to the ground network and to the mission control center. For the Pathfinder mission, the requirements was at a maximum of 30 minutes latency, but this value can be reduced after the assessment of the Pathfinder mission. Of course, since you have not a constant visibility with the ground station, the only possible solution in order to achieve this requirement is an intersatellite link. Such link is not practically achievable directly by the Hermes constellation. Then we adopted a commercial network providing this service. We adopted the Iridium network because such network is currently the only one that provided functionality for the uses with satellites, since all these networks are designed originally for ground communication. The radio network has been used in a series of CubeSat missions performed by NASA along the last 15 years, and provides a very low data latency. The other methods of communication of the CubeSat are relatively standard. We are speaking about the UHF and VHF link that is non-directional, and then is the baseline for the telecommand and the telemetry in LEOP. Once the attitude control is available, the baseline is the S-band that allows a quite large data volume that is required for the transmission of the scientific data. In case of failure, UHF, VHF can provide transmission for the scientific data also, but of course with reduced performances in the data rate. These performances are guaranteed with just 2 ground stations. Of course, such performances in the data amount that can be transmitted to the ground daily can be increased if a larger ground station network is available. Of course, a crucial role in the determination of the position of the spacecraft in the sky is the GPS, the orbital positioning. The orbital position can be computed only with the GNSS services, and then it's crucial to ensure that the correct amount of GNSS satellites is also continuously visible during the mission, and that is the case of the HERMES mission, of course. Since the pointing strategy is vital to ensure the scientific performances, special attention has been dedicated to the design of the DCS, and we provided 3 degrees of redundancies in the actuation, since the actuation is guaranteed by a set of magnetic torques, but also by a pyramid of 4 reaction wheels. So we have a certain amount of redundancy in that. And in order to provide...
Sorry, Two
yes,
more minutes.
Yes, of course. Thank you. Regarding the power supply, we designed, we looked for an optimal design for the solar panels, especially in order to guarantee the feasibility of the mission, both in the equatorial and in the sun-synchronous orbits, in order to allow a future expansion of the constellation along orbits that are different than equatorials. This is just a view of the configuration of the internal satellites with 2 wings in 3 U columns. All of that in a CubeSat that has 6 kilos mass, including the payload. The integration phase of the first triplets is incoming, since we had the critical design review at the Italian Space Agency during October 2020. We expect to end the integration by the end of the next years, 2021. Just to conclude and to make a summary, HERMES, of course, represents an innovative approach to perform space science. It's not something that is exclusive at Spolimi, of course. But what we have designed is something that is applicable also in the long term for space exploration mission. This approach can be applied, of course, with some technical and technological enhancement, also on long-term missions. And the HERMES service module, in the end, is a general purpose platform which can offer to a payload a 1U volume, a mass up to 1.5 kilograms, 5 watts powers, and in, of course, low Earth orbit, 1 gigabit data downlink per day. This ends my presentation, my panoramic. Of course, if you have any question, they are welcome. Thank you.
Okay, thanks, Paul. Thanks a lot. I think we have time for one quick question, if there is any. So if you want, just write down in the